welcome to this screencast on the properties of the secant function. Because the secant function is defined in terms of the cosine function, its values and behavior are completely determined by the cosine function. In this video, we will compute and analyze values of the cosine function to better understand properties of the secant function's graph. To begin, we know that for any real number t for which the cosine of t does not equal 0, we define the secant of t to equal 1 divided by the cosine of t. In other words, the secant of t is the reciprocal of the cosine of t. Let's compute the exact values of the following. We'll start with the secant of 0, so that would be the same as 1 divided by the cosine of 0. The cosine of 0 is 1, so we have 1 divided by 1, which equals 1. Next, let's look at the secant of pi over 6. That would equal 1 divided by the cosine of pi over 6, which is the square root of 3 over 2. So we have 1 divided by the square root of 3 over 2, and that equals 2 divided by the square root of 3. Next, the secant of pi over 4. That equals 1 divided by the cosine of pi over 4. The cosine of pi over 4 is square root 2 over 2. So we really have 1 divided by the square root of 2 over 2. And if we multiply both the numerator and the denominator by 2, this would simplify to equal 2 divided by square root 2. And if we multiply both of those, numerator and denominator, by square root 2, we end up with just the square root of 2. Lastly, we have the secant of pi over 2, which would equal 1 divided by the cosine of pi over 2. However, the cosine of pi over 2 is 0, and we can't have 1 divided by 0, so that means the secant of pi over 2 is actually undefined. We've calculated the value of the secant function at 4 of the 16 special points on the unit circle. Let's plot those on a graph. When t equals 0, the secant of 0 equaled 1. When t equals pi over 6, the secant of pi over 6 is approximately 1.155. When t equals pi over 4, the secant of pi over 4 is approximately 1.414. And when t equals pi over 2, the secant of pi over 2 is undefined, so we won't graph anything for t equals pi over 2 at this time. Take a moment to compute the exact secant values at the remaining special points on the unit circle, and then plot the corresponding points on the graph and try to sketch the secant graph in an intuitive way. Alright, so hopefully you took the time to try to finish the table and graph the points. Take a moment to check your work here. There are a number of important observations we can make that will help us understand the secant function and its graph. So first, we notice that in quadrant 1 and in quadrant 4, the secant function is positive. And this is true because the cosine function is positive in these quadrants. In quadrants 2 and 3, the secant function is negative. This is true because the cosine function is negative in quadrants 2 and 3. Second, we notice that anytime the cosine of t equals 0, the secant function is undefined. So the secant function is undefined at t equals pi over 2 and t equals 3 pi over 2. Let's look more closely at what's happening near t equals pi over 2. We observe that as t values in the first quadrant get closer to pi over 2, the cosine of t gets closer to 0, while being always positive. I'll denote that the cosine of t is getting closer to 0, but still being positive by using this plus sign above the 0. When we have a fraction whose numerator is 1, but whose denominator is getting closer and closer to 0, we know the value of the fraction is getting bigger and bigger. That means as t values in the first quadrant get closer to pi over 2, the secant of t is getting bigger and bigger. Shifting gears and looking at the graph, if t values are getting closer to pi over 2 on the graph, then t is approaching pi over 2 from the left side. And since the secant of t is getting bigger and bigger as t approaches pi over 2, thinking about that first quadrant still, we can actually say that the secant of t is growing without bound as t approaches pi over 2 from the left. That means the graph will look something like this as t approaches pi over 2 from the left. Now, let's also observe that as t values in the second quadrant get closer to pi over 2, the cosine of t gets closer to 0 while being always negative. I'll denote that the cosine of t is getting closer to 0 but still being negative by using this negative sign above the 0. When we have a fraction whose numerator is 1 but whose denominator is getting closer and closer to 0, we know the value of the fraction is getting bigger and bigger. And since the denominator is always negative, this fraction, 1 divided by the cosine of t, is actually getting more and more negative. It's decreasing without bound. That means as t values in the second quadrant get closer to pi over 2, the secant of t is decreasing without bound. So looking at the graph, if we have t values in the second quadrant getting closer to pi over 2, then we're actually looking at t values that were bigger than pi over 2, and now the t values are approaching pi over 2. Notice that t on the graph, t is approaching pi over 2 from the right side. So we can actually say that the secant of t is decreasing without bound as t approaches pi over 2 from the right. And that means the graph will look something like this as t approaches pi over 2 from the right. This behavior that the secant function is undefined at t equals pi over 2 is increasing without bound as t approaches pi over 2 from the left and decreasing without bound as t approaches pi over 2 from the right results in the secant of t having a vertical asymptote at t equals pi over 2. Similar reasoning could be used to show that there is also a vertical asymptote at t equals 3 pi over 2. And remember, we could repeatedly rotate around the unit circle to create more and more branches of the secant function. So noticing that the vertical asymptotes of pi over 2 and 3 pi over 2 are a distance of pi from each other, we can conclude that starting at pi over 2, the secant function has a vertical asymptote every pi units. And we could do this clockwise or counterclockwise. So we could look to the right on the graph every pi units or to the left on the graph every pi units. And we would see a vertical asymptote. We can notice, or we can denote this by writing t equals pi over 2 plus or minus k times pi, where k is any whole number. The vertical asymptotes are also related to the domain of the secant function. So we observe that the secant function is defined everywhere except at the vertical asymptotes. And again, because we could repeatedly rotate around the unit circle, we can say the domain of the secant function is all real numbers except t equals pi over 2 plus or minus k pi, where k is any whole number. Lastly, we notice that the range of the secant function is all real numbers y, such that y is less than or equal to -1 for the concave down branches, or y is greater than or equal to 1 for the concave up branches. Another way to write this would be all y such that the absolute value of y is greater than or equal to 1. And we can also see in the graph and in the table that the secant of t has a period of every 2 pi. So in summary, for the function p of t equals the secant of t, its domain is the set of all real numbers except t equals pi over 2 plus or minus k pi, where k is any whole number. Its range is the set of all real numbers y, such that the absolute value of y is greater than or equal to 1, and its period is 2 pi.